Hello YouTube, welcome to our open forum discussion today. And in the last few videos, I've talked a little bit about turbulence modeling, basically the K-epsilon model, and how the most basic of Reynolds average Navier-Stokes came about, and this LES model, when the most basic of which being the Smagorinsky model, and I've briefly covered some of the concepts in both of those models. In today, I want to cover something a little bit different. Because the thing about turbulence models is that they model the very turbulent part of the flow. And where is most of that turbulence located? So if you were to imagine with me, okay, let's say we have our usual pipe flow situation, or at least a free flow. Okay, we have some boundary, and we'll have some free flow over here. Okay, we'll have some flow here, and you can imagine in the bulk fluid. All right, let's say this is like the center of the pipe, or there is some what do you call it? Yeah, let's say this is a pipe, and then in the center of the pipe, yeah, there is turbulence going on in the center. Now, the thing is, as you go very close to the wall region, so let's zoom in here, you have this thing called the wall region. Now in the wall region, you can imagine the turbulence will have to start to die down somewhere, because there isn't enough space for this turbulence to keep swirling and swishing around. And what we have is this phenomena that near the wall region, it is not turbulent. So near the wall region, it is not really turbulent. But because it is so close to the wall, yeah, we have this thing called the turbulence dies down, and we have this thing called a viscous sub layer. So the term for it is called a viscous sub layer. Alright, let me now this is a viscous sub layer. Now how can we think about this viscous sub layer, and why would you say that there is no turbulence here? So you can imagine very near the wall, right? Very near the wall. Let's say the first layer we have is no slip condition, right? All right, no slip condition. This means U equals to 0. Okay. Now let's say you have a coordinate y which represents the distance going away from the wall. You can imagine, like, let's say in this next layer here, this U will not be equal to 0, but it will be very much lower than, let's say, the U in the center. So I have a U center here, and this will be greater than the U let's say at the near the wall. So if we were to draw a velocity profile, if you remember what a turbulent velocity profile looks like, it looks something like this, okay, where the bulk of the fluid is moving at more or less a very similar velocity. So this is the averaged velocity. So most of it is moving in the center like so, but at the sides the velocities kind of take a dip because of this phenomena. We have this no slip condition here, and then the velocity gradually increases till it reaches the bulk of the fluid. So remember we have a Reynolds kind of a transition, where if we have a Reynolds number, Reynolds number equals to rho into velocity into d over the viscosity, dynamic viscosity. If we have the velocity low enough, the regime will become laminar. So with low U, laminar flow, we have laminar flow. Okay, so where is this low U region? It is near the wall. So why we have the low U? We have this no slip condition, and then we'll have increasing velocity as we get away from the wall. The question is, what is this velocity profile like at the wall? And what's it got to do with turbulence? So remember, we said that near the wall we have a laminar region. It's laminar near the wall, and we call this the viscous sublayer. Alright, so the thing about this viscous sublayer is that we don't have turbulence. Alright, there's no turbulence here. So the thing is that our Reynolds average Navier-Stokes or LES models may not work here. Now, more models are usually developed more for Reynolds average Navier-Stokes. So that's the key thing about this thing. We need a wall model for the Reynolds average Navier-Stokes. Now for LES models in general, there will be some kind of wall correction. It may not take the same form as what I'm describing in this video, but definitely you will not have the turbulence near the wall being the same as the turbulence in the center of the fluid where it is far away from the wall. Okay, so there has to be a way to account for this, and what we discussed in the Smart-Gorinsky model doesn't quite make up for that. So there are going to be extra corrections we need to make, or else we have to use a entirely different model altogether. So yeah, I'm going to first tackle the Reynolds average Navier-Stokes bit. Okay, so this is the wall modeling for Reynolds average Navier-Stokes, and yeah, so let's go examine the thing. So we know there is a viscous sublayer. Let me zoom in. Okay, we call it VSL, near the wall. Okay, so let me put this in blue. Okay, so what are the equations applicable here? Well, let's use the shear stress equations, because that's where we find turbulence, right? So remember, let's say we have tau, okay, tau over rho, okay, so this is the shear stress equation. Tau apparent over rho equals to, okay, nu plus nu t partial, okay, this is for the Reynolds average Navier-Stokes version, partial u partial y. Okay, so this is our standard, equation that takes into account the effects of turbulence as a turbulent viscosity. All right. Now the trick here is, of course, we need to do data fitting. So for the model, we need to do some data fitting. All right. There is in the near wall model, so I'm discussing a wall function or the near wall models, we need to do some data fitting. So this is experimental, right? This is experimental data. So again, when we like to do experimental data with various fluids of changing viscosity, density, etc., we will need to do some scaling. So to prepare, the equation for data fitting, we need to non-dimensionalize. So we need to non-dimensionalize. So, alright. So remember, let's say for example, we have this pipe friction coefficient. So we wanted to experimentally determine the friction coefficient of the pipe as a function of the flow properties. So what we see in general is that we have a chart that describes how the pipe friction changes as a result of the Reynolds number. So these are non-dimensional quantities, and of course you have surface roughness as well, which will give you different kind of curves. So for example, you recall this general what do you call it, graph. It's a very common graph where we see the fanning friction factor, or whatever kind, can be Darcy or Moody or whatever. It's compared against the Reynolds number, and for various different surface roughness we have different values of the fanning friction factor, so they have different curves. So now this is the idea, so that this is of course for pipe flow, the overall pipe flow, but we can use a similar methodology for this wall region modeling. We can use similar methods for wall modeling, wall region modeling of viscous sublayer. Okay, so we can start non-dimensionalizing. So what kind of scale will we want to use? Characteristic velocity. So the things we want to non-dimensionalize are U and Y. So what is a good velocity scale or characteristic velocity? Okay, so one of the very good velocities we can use is this thing called friction velocity. Okay, I'll just explain in a bit. Okay, we just let's take a look at this equation, and we take a look at the dimensions. So this kinematic viscosity is meter square per second. This is the dimension of meter square per second, and du dy will be in the dimensions of 1 per second. Okay, 1 over time, as we discussed in the last video. Okay, so this is actually meter square per second square. Conveniently for us, when we take the square root of this value, this so-called shear stress, dynamic shear stress divided by the density, we can get some kind of friction velocity. We can get some kind of velocity. If you take the square root of this, the units become meter per second, and then we can get some sort of characteristic velocity. We call this the friction velocity. Why is it called friction velocity? Because this shear stress is what is kind of dragging the flow. It is the friction is causing the velocity near the wall to slow down and stop. So I mean, the only thing slowing the velocity down is this shear stress, and it's going this way, right? So that's how it is. Okay, so tau apparent divided by rho, and then we take this to the power of half. Okay, now, well, which tau apparent are we going to use? Okay, because at different points of the fluid, in the viscous sublayer, we're gonna probably have different tau apparent, right? Alright, we're gonna have different tau apparent as we go from, let's say, this point in the fluid and this point in the fluid, and of course at the wall as well. So for sake of convenience, or it's a good for the sake of a good reference point, of having a good reference point, okay, so we take tau apparent at y = 0. This is at the wall. Why do we do that? Because at the wall there can be no turbulence. So nu t equals to 0. Okay, so this is what we have, tau wall. Okay, so tau wall equals to nu into the average velocity gradient. So this is the friction velocity. Okay, I need to do a square root on this. Friction velocity. Okay, some people like to use this notation. For example, in Adrian Bejan's Convection handbook or Convection textbook, it will use this kind of a notation. So this is the friction velocity with which we can non-dimensionalize u. So we have, so for u or u bar, the non-dimensional form is u plus equals to u bar divided by u star equals to u bar divided by this friction velocity here. That's all we are doing here. Okay, so now the next step is that we want to non-dimensionalize y as well. We also want to non-dimensionalize y. Okay, so what is the appropriate length scale? Okay, so for starters we already have, let's make use of what we already have. Let's make use of what we have already. So we have a characteristic velocity, we have a characteristic friction velocity. Okay, so u star is this much, and this is in meters per second. Okay, so now we need something, some sort of length scale. So how can we make this into like some sort of length scale? Alright, so one good length scale is this. Okay, we know that the viscosity nu, it's in the units of meters squared per second. If we take this viscosity, kinematic viscosity nu, and we divide it by this friction velocity, we will just get meters. Okay, so let's have a length scale in meters. Of course, it can be in other kinds of scales as well, like feet or whatever, but I'm just going to use meters because SI units are convenient. So I'm going to use the this viscosity, and I'll just divide it by the friction velocity, and that will give me a length scale. Okay, so it's nu over u star. That's all. Okay, u star. Okay, so when we substitute this back, we can have a non-dimensional form of this equation. Okay, you can substitute this back to get a non-dimensional form of this equation. Okay, so I'm not going to substitute in this video. I'm going to do it in the next video. So stay tuned. I'll get to more of this modeling stuff. More modeling stuff. Thanks for watching. I'll see you guys again. Bye bye.